Okay, so let's look at boiling point and kind of the rest of the phase changes really quick. Boiling point, this is the point, a temperature at which a substance vaporizes. Okay? The temperature, this is interesting, the temperature will not increase until all the liquid is vaporized. So if you look at this this is kind of like a melting boiling curve here. So here is here it is, boiling point. Okay, this is a temperature on the side here. Notice you had a plateau, okay? So the temperature doesn't change. So until all the liquid has become a gas, the temperature actually remains the same, okay? And then when all of it has become a gas, then the temperature can increase. So that's just kind of interesting. So when you boil something, it remains at that temperature. The critical point. This is when a liquid is sealed in a container while heating and vaporization occurs. So it says right here, as the temperature rises, more of the substance vaporizes and the pressure increases. Okay, so we seal a container, okay, and you heat it. So it's kind of like boiling evaporation. So I have, let me use this color here. Here's my glass of water now. You put a lid on it. Lid. Okay. Here's my water. Okay, here's my fire. Fire. Okay. Here's my fire and I'm heating this. Okay? Now, as I'm heating this, these water molecules are going to become very energetic, okay? And start vaporizing, okay? Because it's getting really hot. It's boiling, okay? Think about when you're boiling water and you put a lid on top of that, okay? Eventually, this lid starts going crazy and the water starts like coming out of the side and it's just all sorts of chaos going on. I mean, that's what's happening, okay? But we seal it, okay? So our lid can't come off, okay? So it's wanting to explode. There's all this energy into it. So now I have all of these molecules up here. Remember, the more molecules I have vaporized, the higher the pressure. Okay? So I'm causing a very high pressure. Okay? You see here, as more of the substance is forced into to vaporize, the density of the gas increases while the density of the liquid decreases. So that makes sense. Basically, it's saying as the temperature increases, more of the molecules will vaporize, okay? So the gas will become heavier. So basically there's more gas and less liquid, okay? So basically more of the liquid is becoming gas. That's all that's saying, okay? The gas and liquid phase begin to disappear and a supercritical fluid forms, okay? And at this temperature is called a critical temperature. So you have to have it sealed, and basically what happens, this liquid is starting to become a gas, okay? And the density of the gas is increasing. Basically, there's more gas. And the density of the liquid's decreasing because it's all going into the gas phase, okay? And at some point, this is called the critical point, all of a sudden your gas and your liquid kind of disappear and you have this supercritical fluid, which is really neat, and it has properties of a fluid and of a gas. Okay, and there's this video I'll post on here that you could watch about a supercritical fluid that's actually pretty interesting. I don't know if this link will work. I don't want to try it right now because I'm afraid it'll, mess up my whole computer. But I'll post it and you can see like some of the things they're doing with supercritical fluids. So that's the critical point. The critical point basically whenever you have a substance that's not quite a liquid and not quite a gas. It's kind of in between. It's hybrid. Okay, so other phase changes. There's sublimation. This is when you go directly from a solid to a gas, okay? Think about dry ice. Okay, you have these solid dry ice, and what is it? It's going directly to a gas. It never forms a liquid, right? It goes directly to a gas. And it just means that some of the molecules have enough kinetic energy to go directly to a gas, okay? So it goes past the liquid. Deposition is the opposite of this. This is whenever it goes straight from a gas to a solid, okay? You can see this with snow, okay? You have these water vapors and it turns directly into a solid, okay? Anyway, so it's just another phase change. So sublimation is directly from a solid to a gas, so that would be considered endothermic. And then gas to a solid, which would be exothermic, which is deposition. Fusion, or as we kind of know it as melting, it's whenever you heat a solid, okay, and it will fuse into a continuous liquid, okay, so it melts. So basically, it goes from a solid to a liquid. At the temperature, when the molecule have enough thermal energy to overcome the intermolecular forces, they become liquid. So you have the solid, and they have all these intermolecular forces, okay? Now, whenever you put enough energy, in our case, heat into it, it breaks the intermolecular forces, and it becomes a liquid. Okay, so the stronger the intermolecular forces, the higher the melting point. And then freezing is the opposite. Okay, you go from a liquid to a solid. So this is exothermic, so you're releasing heat here. Okay, so the temperature is lowered enough that the kinetic energy of the particles decrease and they become a solid. Okay, so they were up here, they're very energetic, they're a liquid, or at least decently energetic. Okay. Then you start to cool it down. Anytime you cool, it's going to lower the kinetic energy. You lower the kinetic energy so they're not as energetic. So they become more solid-like because they can reform their intermolecular forces, those interactions. Now what we're going to start looking at is what's called a water curve. And so basically, anytime you do a phase change, whether it be melting, freezing, vaporization, deposition, any of them. Anytime you do any of the phase changes, you're either going to need energy or you're going to release energy. So there's a way to calculate that. And what we're going to look at, so here's the energetics of freezing and melting. So the amount of energy required, 1 mole of a solid, is called heat of fusion. And there's a table that has all of them. For melting, it's a positive sign. Why would it be positive? Because you're going from a solid to a liquid. So anytime you become more gas-like, so if you go from a solid to a liquid to a gas, you're always endothermic because you need heat to melt, right? And in freezing is the exact same number, right? Because it's the same actually energy to melt and freeze because it's the same process, just backwards. So freezing is negative because it's exothermic, because you want to release energy. Okay, so let's think about this. So our energy cannot be created nor destroyed, okay? So the amount of energy it takes to melt something is the exact amount of energy it takes to freeze something, okay? Because they're just the opposite sort of reactions there, okay? So if we look at this, you can actually do a heating curve. So I could ask you, okay, how much energy does it take to heat up a substance from 0 to 100 degrees? Okay, we can look at, in this case, we're looking at water. Okay, so you have to hit every single one of these points. So you're going from 0, you're going from the melting point, and then you're going up the curve here, and then you're going to the boiling point. So you're going to have 3 different points there. Anyway, so we're going to look at this. We're going to, so there's ice warming, so that's right in here, it's warming. Then it melts, so you're going to go up as it warms, then it melts. Liquid warming, it's warming, warming, warming. Then it's vaporized right here, and then steam warming. Okay, so anytime you're going up, you're warming. Okay, anytime you hit like a melting point or boiling point, that's a different thing there. Okay, so we're going to look into all of that. Anytime you're warming, okay, your formula is MC delta T. Do you remember that? That's for Q, right? Q equals MC delta T, okay? So that's the formula you use. Anytime that you're at a melting point or boiling point or freezing point, you're going to use Q equals N delta H. Delta H, because we actually have that calculated, it's in a chart. N, because you need the amount of moles, okay? Because, delta H is in kilojoules per mole, okay? And we don't want per mole, we want per kilojoule. So you're going to multiply by the moles. So Q is in delta H anytime you hit one of those points, okay? So, for example, if you calculate the heat required to melt the ice from negative 25 to 0 degrees Celsius. Okay, so if we come back here, okay, here I am. I'm starting at negative 25, so I'm starting about right here, and I want to go to 0, okay? So from negative 25 to 0, I'm at a warming stage. But whenever I hit 0, now I'm at the melting point stage, okay? So anytime you have to look at your numbers. So if I, for example, say I want to go from negative 60 to 120 degrees. So think, how many calculations do I use? Okay, and here are all your formulas here. MC delta T, infusion, MC delta T. So here are all your delta H's. Here's all your C numbers for the different stages. So this is a really good summary table here. Okay, so if I'm going from negative 60, I'm going to have one calculation all the way up to 0. Okay, so that's 1. 1 at 0. Okay, so that's 2. 1 going up to 100. That's 3. 1 at 100. That's 4. And then 1 going up to 120. That would be 5. So you would have 5 different calculations. So anytime you see there's A is this green line. It goes up to 0. And if you're at 0, you have to calculate 0. And then C, E, and F. So the next one, I think the next 2 vodcasts will go over more of this and do some examples of what I'm talking about here.